So let me just start this here. I tell you in a few seconds we will be online. And as usual, I introduce us, you introduce yourself. In a few seconds we will be on. Okay. So good afternoon. Thank you for joining us. This is Essence of Science, and we have a returning guest. Is it fair to say Professor now, David? Professor David Garrison, joining us from a physics department in Houston to talk about nature of time. And please go ahead, David, introduce yourself.
Yeah, my name's David Garrison. I'm a professor at University of Houston Clear Lake. I'm interested in this topic because when I was in graduate school, I was at Penn State and I was studying in the Center for Gravitational Physics and Geometry, where we talked a lot about general relativity, about how space-time works, and that includes a lot of things about time. So this is a topic that's really fascinating to me too.
Yeah, and that's something that generally nobody really think about it. We just one day somebody gives us a clock and tells us, this is the clock. This is you wake up at this time, you go to bed at this time. We have breakfast, lunch, and dinner around this time. You have to be certain places around same time. Alone to understand that when it's morning with us, it's late night somewhere else. That already was for me an eye opener, and so. But um, I don't believe anybody really thinks that is like air. Nobody really struggle to say air. It's always there. It's just something that we get to live with. When did you first time in your life talk about time? What it really is, and not professionally, but as a person?
Yeah, I think that for me, it was when I started reading about other people who were struggling to understand time. Because the thing is that it's one thing that we just don't understand. I mean, it's one of those things in physics that nobody understands it completely or has solved it. There's a lot of ideas about time. And then when you start reading about it, there are people who have been struggling with time for forever, literally. For me, I think the idea of time, I can't even think about the first time when it started becoming an issue for me where I really thought it meant something. But I think it may have been when I was first learning about Einstein's theory of relativity.
How old were you when we were thinking about Einstein theory of relativity?
Well, and the reason why is because before Einstein's theory of relativity, everybody just assumed that time was just this constant. It was the same for everybody in every situation. And so it was like air. It was like it was there, but it really didn't do anything. And it was, but with Einstein's theory of relativity, it started out this idea that time can actually be different for different people in different situations. And then when they got to Einstein's general theory of relativity and going into cosmology, we get to the idea that time actually had a beginning and time has an end. And so it's not even something that is always going to be around and it's an immutable property. It's a physical property of the universe we live in.
It's not linear. It's not like, the chunk of time, chunk of time, chunk of time. Tell me about it.
Yeah, well, the idea from Einstein's special theory of relativity is that as one observer moves faster, time slows down. And when you move all the way up to the speed of light, time actually stops, which seems very, very weird. But at the same time, as you go through life and you get older, you do sort of notice after a while that time doesn't feel the same as it did when you were younger. Like when you're a kid, it seems like 5 minutes is forever. But as you get older, it's like a blink of an eye, and you're thinking, years, and you could think, a year doesn't even feel as long when you get older. And it's because you have so many years behind you that it just doesn't feel the same way.
Percentage, like for a 5-year-old child, 1 year is that 20% of their life, whereas for me, it's just 2% of our life.
Yeah.
So yeah, that the psychological side, kind of the perception of life is a absolutely amazing thing for itself. But as well, the idea that this time, all what we notice is the passage of time, not the time itself. Like sun goes up and down, or we get hungry, or something happens. That is what we notice. Like now, let's say you're in the middle of the space, there are no stars around, or there's nothing around that you make you understand the passage of time, and you're just floating. And
Mhm.
there is still a physical thing that's called time, or is it?
Yes and no. That's a good question. It's because according to Einstein, time by definition is the thing you measure on a clock. It almost seemed like a cop out, but that was how he defined time. And so, in theory, according to him, if you get rid of all clocks, you get rid of time. But here's the trick: a clock can be almost anything. A clock can be oscillations of a light wave. So it can be if you can see light, or if you can hear a sound, or if any processes are working, where every process is oscillates, everything process moves back and forth. And that kind of goes back to the joke about physicists where when we were going through and learning physics as an undergraduate, one of the first things they would have you do is solve the simple harmonic oscillator, which is just an oscillating system. And then you go on and you study quantum mechanics and you study this simple harmonic oscillator. And then you do advanced classical mechanics and you study a simple harmonic oscillator. And then you do electrodynamics and you study these oscillating light waves. And after a while, you keep asking yourself, why is it we're always studying these harmonic oscillators? And it's because, first off, it's the only thing we really know how to solve. And secondly, because everything kind of comes back to being an oscillator. So our whole concept of time comes from something oscillating. And anytime you have anything oscillating, you have a clock.
As a matter of fact, that is how we measure time, right?
Yeah.
From the ancient time, that they have a drop of like old kind of, I mean, started with the oscillation of the Earth's rotation, the position of the sun was how we measure time. Then they got more advanced, like Galileo measured the drop of the water, that repeating drop of water as a passage of time. As a matter of fact, I'm not sure if it's true or not, that when Galileo came with the idea of this pendulum, he was measuring the pendulum against his own heartbeat. And,
Yeah.
and then later on, it was the pendulum, that oscillation of the pendulum, then the oscillation of a rotating wheel, and then they made it the wheel smaller and smaller.
Yeah. And the current definition of a second, I'm reading this right now, is 9,192,631,770 periods of the radiation corresponding to the transition between two hyperfine levels of the ground state of a cesium-133 atoms.
Well, that
So
is
they literally,
that's
this is how,
explain that. What that now? Practically, you're saying we made it a way for measuring the time with the sun and Earth's rotation, which are variable. We know now.
Mhm.
Same, like a day is not always the same, and a year is not always the same. As a matter of fact, there are lots of variation there and so on. And we are physics got so good, our measurement got so good that those things weren't accurate enough. Now we take the actual some physical characteristic as a measurement of time. But that what you just said, it's way above my head. Explain to me what that really means.
Yeah, so I guess the reason why they're using cesium 133 is because I believe that's what they use in atomic clocks. And so the idea is that the atomic clock, instead of it being based on something that might be arbitrary or might be changing, they wanted something that could be as stable and consistent as possible. So that's where they came up with that idea. So we have this oscillation that comes from the radiation produced by this tiny little quantum mechanical thing, and we've just defined a second as that number.
Okay,
And
you mean
a
what
lot of other units, like the unit for a kilogram, are measured also like in the same kind of way.
no, but what does oscillation mean? Okay, it's atom. There's a nucleus, there are these clouds of electrons. What do you mean by that oscillation? What is that?
Yeah, well, so what happens is that when you transition in an atom and you go between two states, what's happening is an electron is going from one quantum level to the next quantum level.
Meaning the
In order,
electron jumps in the orbit. Is that what?
right.
Okay.
In order for that to happen, it has to release energy or gain energy if it's going the other way.
Mhm.
And so when it does that transition, it's producing basically a beam of light.
Mm.
And that, or we call it a photon. And so when that photon is emitted, what it's really doing is a photon, for the viewers, we call it that in quantum mechanics because it's just a unit of light. But in electrodynamics, what's happening is that photon is really an oscillation between the electric and the magnetic field. So what happens is there's a tiny bit of electric field and it increases and it increases and it goes up and then it goes down. And while that's happening, there's a tiny magnetic field that's being created perpendicular to that. And it's going up and it's getting bigger and it goes down. And eventually it goes down and it goes in the opposite direction. And so they keep oscillating back and forth between the electric field going up and the magnetic field going up, and then they go down and then they go in the opposite direction and they go back and forth. And they're doing this perpendicular or what we call transverse to the direction the thing is flowing. So if the light beam is coming right at you, the electric field might be going up, the magnetic field might be going horizontally, and they're just oscillating like that.
Yeah,
So
yeah.
even light is just an oscillation, and that oscillation, that flipping back and forth
So
takes time.
is that fair to say this is a different level of energy of the electron in the atom, and it's so regular in cesium atom, and we
Mhm.
look at it. We can obviously this photon doesn't need to be a visible photon, can be a invisible photon, but because number one, this oscillation in cesium atom is so regular and we can measure it, that is what we choose to be that. Is that fair to say?
Yeah,
Now,
that's exactly right.
I remember my father used to have these mechanical clocks. And when I was a little child, all of a sudden we have these quartz watches. And then there were, I mean, everybody was crazy about this quartz watch because they were cheaper and you can put it and it would show you the thing and so on. And is it similar thing with the quartz, but it's less accurate than cesium? Is it the
Yeah,
kind of thing?
yeah, because basically what happens is crystals like quartz, the reason why we use those as clocks is because a crystal has a very regular lattice. It has all the atoms are in very specific places with regards to each other. And because they're in such a regular, uniform shape, if you had, if none of these crystals had any defects, they would all be exactly the same. And so you could buy a quartz watch and I could buy a quartz watch and they're both the same thing, right? And so what happens is because they're the same, they will tend to vibrate with certain regular frequencies. Like if you tap it and it vibrates, it's going to vibrate the same, but it's going to vibrate the same as mine because they're the same thing. Um, but the problem is in reality, there's little defects in the crystals, kind of like when you buy a diamond, there are little defects in the diamond. It gives them a different kind of shine to it. What happens with the cesium atom is it's so small that there's no defects.
I see.
So it's even better and more regular. So the bigger we make things, the more likely they are to have defects and flaws in them, which are going to cause them to not vibrate the same. And then that's going to throw things off.
Now, this is what I understood about the quartz watches, that
Mhm.
literally mostly ladies would get a quartz crystal and take a small fraction, they break it and make a small piece of it, and they put that small piece of quartz, actual crystal, the best they can find, between in an electric field, like put an electrode on one side, electrode on the other side, and give it literally an electrical, like a push, not a called push, but the electric push. And on the other side, they would measure the variation of the electricity that comes out, and that would be a regular or regular enough to measure time. And I have even seen that when they started that, actually in 1950, they started for the war, for the like creating this radars and so on. That is when they started that all these ladies in their 1940s attire, sitting on a desk with a small little chisel and hammer and so on, chipping small crystals and so on. But then 20 years later, they end up, being, the technology would be mature and cheap enough to use it in other things than a military kind of thing. Now, what makes the cesium preferred to, like, we have like so many different elements on what makes cesium so preferred there?
Yeah, I'm not sure. I'm not sure why they would pick cesium over something else, but I'm not sure if it's a cost issue or if it's just some other characteristic of it.
Yeah, well, but many times I know that people just try different things without really understanding what is the truly underlying reason. But
Yeah.
then they figure out one thing works so much better than the other. But I have heard that you can use an atomic clock to actually measure distance from Earth core, meaning that if you bring it 2 feet up, you can measure it that you have moved it 2 feet up. That's crazy. Is that
Yeah.
true?
And that would be true because that goes back to general relativity, where another thing that Einstein did was he basically said he came up with this thing called the equivalence principle. And the equivalence principle said that when you're accelerating, you don't know whether you're in a gravitational field accelerating or if you are in space in a rocket and you're accelerating. It feels the same way. And so you can't tell if everything is dark and you can't look out and you can't see anything around you, you don't know that you're not experiencing gravity. And when you go to the amusement park and you ride on a fast ride, it's the same way. You can feel yourself being pulled back or pushed back in the ride, and it feels just like gravity. So what happens is that according to Einstein's special relativity, you got this slowdown of time that occurred as you move faster and as you accelerate. So what happened was in a gravitational field, if it's equivalent, then time should also slow down in a gravitational field. This was amazing because it seemed like the kind of thing that seemed completely unmeasurable, but it's actually the basis of our GPS system. Our GPS would not work if this were not true, because as these satellites are in space, they're very much higher up than we are, and the time moves differently for them than it does here on the ground. And so if they did not correct for general relativity, we would get the wrong answer on GPS, and you could not do things like you couldn't see where something is precisely. So if you have really good GPS system, you can tell exactly where you are on Earth's surface, and you can also tell if you're going higher or lower or what the altitude is and everything.
No, well, I have heard that if you wouldn't correct for the Einstein relativity, formula, the accuracy of a GPS go from 1 foot to half a kilometer, or
Mhm.
100 to 500 meters. That is the difference that makes the idea adding those relativistic thing and so on. And that's amazing by itself that this, obviously, what the GPS does, right? I think each of them, they have a clock, very accurate clock, and they send a signal. and your device measures the signal, the time that sent to you, and say what is the difference. So that must be your distance to that satellite versus that satellite, that to that satellite, and knowing exact accurate location of those satellites practically triangulate
Mm-hmm.
distance, and then they use a fourth satellite to confirm that. And as many of the things that we use is based on military development, and I believe it hasn't been that long, just 20 years ago or so, that finally US military moved to a different system and gave the whole capacity of the GPS to civil, kind of purpose for civil
It was
purpose.
probably, yeah, it was probably 20 to 30 years ago. I'm not sure exactly when, but yeah, that's when all these GPS devices started showing up, because before that, they weren't accurate enough to give turn-by-turn directions.
Yeah,
Like
yeah,
you said, 500 meters, you've already missed your turn.
yeah. But they weren't accurate because military didn't allow us to be accurate. They made it easy
Right. Yeah,
for
and that's the thing. They didn't allow that accuracy, but it's a really brilliant thing because it relies on a constellation of satellites
yeah.
so that at any given time, anywhere on Earth, you can at least see the four satellites. But you're really probably seeing a lot more than that on your device.
And it all comes back to time, and equal that we divide time in equal, measurable, repeatable, reliable chunks. But I was always asking myself, is there a smaller unit of time? Is there? What do you think? What does physics
Uh,
say today?
yeah, see, that's the thing is there, according to physics, um, there's this thing called a Planck time. And the idea is that if you take Planck's constant, Newton's gravity constant, the speed of light, all of these are fundamental constants of nature, and you play around with them, you can create different units. So you can create a unit of time, you could create a unit of distance, you can create a unit of length. And what happens is that you create a unit of time, and this unit of time, time, by the way, one of the definitions of time in classical physics is that it corresponds to energy, because where we get the law of conservation of momentum, for example, is because velocity doesn't change as you move through certain things. The conservation of energy comes from something like that with time. So it's basically saying that this thing is constant in time. And so when you look at a really short time, you look at very, very high frequencies of electromagnetic radiation or light, and that corresponds to very, very high energies.
Mhm.
So what happens is, as you go back, to smaller and smaller pieces of time, they correspond to higher and higher energies to measure that time. And at some point, you get to an energy so high that you can never produce that much energy to probe that small a scale of time. And time effectively doesn't exist below that level because we don't have enough energy to even see
Yeah.
time at that level.
Yeah. Now, so I read it somewhere, and I'm not sure, you correct me if I'm wrong, that obviously the space is quantized according to
Mhm.
the most, that, and the smallest unit of space is a Planck distance, which is what, minus 34 or 35, 10 minus 34. And to understand that, a whole atom to the universe is the same like a Planck distance to an atom, something like
Right.
that. That's what I heard. Now imagine now you have this unbelievably small space, and you have a constant speed of light. The time that for the light to take to traverse the Planck distance must be, by definition, by nature of it, should be the smallest meaningful measure or a unit of time. But why it doesn't make sense to me, that I mean, I just cannot wrap my head around it, is that, but that time and that space they can be contracted and distended, depending on in what speed that thing itself is moving around. And I cannot just wrap my head.
Right. There was actually an idea that came from Lee Smolin a few years ago, actually probably 20 or so years ago, and it was called doubly special relativity, as
Okay.
if regular relativity wasn't confusing enough.
Yeah.
So the basic idea was that in addition to having a speed of light that was the same for every observer, which is, people say relativity, they think everything's relative, but the thing is, and for relativity to work, the speed of light has to be agreed upon and the same for everybody. What he did was he also said, well, the Planck units, like a Planck mass or a Planck length, is agreed upon same for every observer.
Hmm.
And the reason why there was a motivation for doing that was because they were looking into the idea of quantum gravity, the idea that gravity is quantized, which, by the way, we don't know if that's true or not. But if it is true, then something special happens as you approach the Planck scale,
Okay.
and you get to gravity behaving like quantum mechanics.
Okay.
And so if that's true, the Planck scale has to be the same for everybody. You can't have one object which is obeying quantum gravity and another one which obeys classical gravity. They have to both be either quantum or classical, so they both have to cross this threshold at the same point. And so that means that that Planck length is going to be a Planck length no matter how fast you're moving.
Okay. Well, again, these are things that I think our biology is not made to understand that intuitively what they really mean. This is mostly mathematical construct that it works like. I think I know that regarding quantum electrodynamic, one of the famous the Feynman thing is shut up and calculate, right?
Yeah.
Don't
And,
expect to understand that. It's just a follow the mathematics to get accurate result for your daily work, and that daily work is GPS, is the monitor, the internet, the processor that are working. It really works, and trying to understand that, I think our biology is not really equipped with that.
Well, and the thing about it is that's why when you start looking at time, you have to go beyond looking at physics and you have to look at other areas because there's other areas that people have tried to understand time outside of physics. And for example, in the humanities, the best example I could think of is in music. Because if you think about it, in music, music is all about time. It's all about notes. It's all about frequencies at different frequencies and harmonics and things. And so when they think about time, they're thinking about, a progression of a song where it just kind of fits a certain pattern and rhythms and things. And so they're playing around with time and they're experiencing time and they're understanding time, but it's not the same physical way that we might calculate. And then if you look at art, I mean, there's a lot of art where they try to understand the nature of, time, and philosophers will talk about contemplation, and you have, people who are meditating and the meditation, they're basically shutting down thoughts in their mind.
Hmm.
And at a certain point, they get to a point where time disappears for them. And that's why you could have these people meditating for hours, literally just sitting there with their
No.
and things like that. So it's kind of it's a human thing to wonder about time. And it's a very many ways of going about it.
Well, I remember I asked you when was the first time you contemplated to understand time. I can't tell you which was mine. I was probably 10, 11 years old. I was looking at an actual clock and I was looking at that second, the arm that counts the second, and I was meditating to see if I can make it stop. And obviously it didn't stop. And sort of I had to accept there's something there that is just there without me trying to change it. I cannot really change it. But then just about few years ago, about 10 years ago, I started listening to audiobooks. What I noticed that slowly I sped it up, like, I went to 1.1, 1.2, and now I'm listening at 2.5 times. That sounds normal to me, where other people say that's crazy. How can you understand anything? But I went slowly up. Now, if I go now, I listen to a book at the normal speed, it sounds to me as if you would slow down and people start slow. And that's completely unnatural to me. 2.5 is a natural thing I listen to book. Now, if I try that with any kind of music, or if there is a book that there is a music into that, the music comes completely unnatural. So even though I have used to listen to these audiobooks at 2.5 speed, the music part of it seems to be governed by some other area of my brain. There is no way I can make the music sound natural to me at 2.5 time of speed.
Yeah,
So
and that's weird because it's like when you listen to poetry, for example. I mean, there's a natural rhythm, and it's like it's supposed to be at a certain rate.
yeah,
And that's where I think that there's an aspect of human perception that comes into this, kind of like with quantum mechanics, where when you observe a particle, you put it into a certain quantum state. And you've collapsed the wave function, they call it, and now it's not in many states, it's in one state. And so I think that there is a human aspect to it in terms of observing and time kind of going together, but we don't really understand that either. Like
are you
how or
describing now the Copenhagen interpretation that reality exists because we are observing it? And now, and the thing about this thing that certainly, if we wouldn't look at this natural phenomenon, we wouldn't be quantizing it. We wouldn't be even developing anything about that. But let's come back to nature of time. Now, you said when you go up to the speed close to the speed of light, the time flows slower and slower, and at the speed of light, time stops.
right.
Does that mean if I look at the star that is, or galaxy that's a billion years ago, for me, that photon, that light of that star or galaxy took 3 billion years to come to me, but the photon left that star 3 billion years ago, and boom, right now he's here, because for that photon, time doesn't exist. Is that what
Yes,
you're saying?
exactly.
That-
So if you were to go, let's say 99.99% the speed of light,
Okay.
and it took you a billion years in our time to get to that star, it might seem like it didn't take that long to get there for you. It might seem like it was only, you know, a few months or a
Oh,
fraction of time. And if you could go even faster, it would feel even shorter.
yeah.
So even though, and that's the weird thing is that like if you could travel at 99% the speed of light and you could go from here to the next solar system and then turn around and come straight back, it might, everybody you know here will be years older. I mean, they might be, say 5, 10 years older.
Yeah.
But for you, it might only feel like you were gone for a week.
Yeah, that is like that part in Interstellar. They went to
Hmm.
that water planet. They were just there for 20 minutes, an hour or so. When they came back, the guy who left on the station, it was 25 years later or 20 years later for that person. That's another piece of time that we don't really, um, we cannot wrap our head around that. But what we are as a biology is a chemical process. Is that fair to say? Like,
Yeah, we're literally made of clocks, if
mhm.
you want to think of it that way. So we've got all these little clocks in our body, like when our DNA is replicating, it's like it's a clock.
Even the
It's
speed of our thoughts is a biologic clock.
in our thoughts, the neurons firing in our head, that's a clock. We're constantly observing light, which is another clock. We are like every time we breathe in and breathe out, that's a clock, our circulatory system. So we're full of clocks. We're made of clocks. So it's kind of hard for us to get away from all time because we can't get rid of the clocks.
Okay.
And
So,
so yeah, and so what happens is that you wonder, even if you look at just anything, any atom, it moves around because of the heat and the energy it has. And so even so atoms are going to naturally oscillate, and because they're oscillating and they're moving, that's a clock. What happens when you get down to absolute zero and
yeah,
you freeze something to all the way down to 0 degrees Kelvin? And for the listeners, what that means is that um, you can think of temperature as the average energy of a system. And so as you have something that's really hot, it means there's a lot of energy floating around, and that causes everything to get excited and bump into each other and so on. As you get colder and colder, what happens is things get less energy, so they don't bump into each other as much, and there's less going on. And then as you get all the way down to absolute zero, it means that everything is technically stopped. There is no energy in the system.
but
So
is
we
that
haven't gotten all the way to absolute zero, but we've gotten close. And when we get close, what happens is when you stop a lot of that energy, you just see the pure atoms or particles themselves, and they start behaving differently. They can start to group together into what they call an Einstein-Bose condensate,
yeah?
and it becomes a whole different state of matter when we don't have that activity.
Well, that is another amazing thing that I always struggle to understand. It is practically impossible to get to the speed of light because further you get, closer you get to that, your actually the energy you have add to your mass, and your mass goes to infinity. Your mass become, in the ginormous. The same way, further you get to the absolute zero, harder it is to move you more in that direction, and so on. So I just, my intuition says there's something connect these two things. These two things are not two different things. It's the same nature, fact of nature, laws of nature that governs that you cannot get to the speed of light for the same reason you cannot get to the absolute zero. Am I on something, or is it just a random facts?
It's it probably is. I mean, one thing it does tell you at a minimum is that there's just certain limits in the universe that you cannot get beyond this threshold. And it's just because of the way the universe is made, is that you can't, you cannot get, you can approach this point, but you can't really defeat it. And then, like with the speed of light, you can't really get beyond that. I mean, in general relativity, they've shown people have kind of looked at ways to kind of get around this barrier, but it involves doing some really interesting things with time and space. So, for example, when we call the horizon around a black hole, is really means that you're getting to the point where the escape velocity of the black hole, how fast you need to move in order to get out of the black hole, exceeds the speed of light.
Mhm.
And so, because of that, light that's inside of the black hole can't escape, so we can't see what's inside of it. But we can actually, apply our physics and we can look at what happens beyond this horizon. And what we see is that if you consider time to be a dimension like space, like if you think about it as there's the direction that you're moving towards the black hole, and you can imagine time being an imaginary direction that goes in this direction, right? If you draw it as a diagram, what happens is that as you flow towards the black hole, you can think of your motion as being kind of a line that goes between these two dimensions. So going straight up in the time direction means you're not moving physically in space. And as you move at the speed of light, you're basically at a 45-degree angle between time and space. And what happens is as you pass that horizon, time gets shorter and shorter because time is slowing down. And space also changes. And then it gets shorter and shorter. And then what happens is as you hit the horizon, those basically disappear to zero. but then on the other side of the horizon, they flip. And so time becomes space and space becomes time.
Is that that famous scene in Interstellar that the main guy falls in a black hole and then he's in this fantastic place that when he physically moves, he's in different time period. Like, it's in the same library. It's not the that he's not the physical space motion. His physical space motion translate in the actual motion in time, that in one area of the library, the child is like a 10 years old and then become older, and then that's the astronomer, then it's grown up and come back and understand the communication and so on, and the gravity is the only thing that can traverse that gap and so on. That's how they communicate and so on. So it is, again, that's another area that we cannot understand, that when you go inside of the black hole, our theories are saying that the time and space flip. What we consider as time becomes space, and what we consider as space become actually time. Again, another crazy thing that I don't believe we are going to have an answer. No, but what
Yeah, yeah, and the thing is that movie is a great example because the technical consultant on Interstellar was Kip Thorne, who won the Nobel Prize for detecting gravitational waves, and he actually wrote an incredible book on space-time and how it works. And he is one of these people who he studied under John Wheeler,
who
who
said
was
who said the time is universe way for everything not to happen at the same time.
right. And also John Wheeler was the one who coined the term black hole,
Yeah.
and he was Richard Feynman's thesis advisor. So
Mhm.
actually, it's had several students win Nobel Prizes. But that was one of the great things, was that he knew what he was talking about, and he did in Interstellar, the images of all that were done in such a way as to show how the human brain might make sense of a world like that, where time and space are flipped, because we're going to still be perceiving what's going on. It's just a matter of how do we perceive this when we've changed the dimensions.
With the difference that I think, based on what we know, if somebody will fall in a black hole, long before he get to the singularity, he's going to have to go through that spaghettification. What's called
Spaghettification.
spaghettification. So by the time he gets reached to the center of the black hole, he's a stream of photon. So there is no actual physical thing that can perceive that. But just to say that, what that really means, explain to us what that spaghettification really means, actually.
Yeah, yeah. So for a black hole, spaghettification means that what's happening is that you're getting pulled into the black hole. But unfortunately, especially with a smaller black hole, smaller would actually be more painful than a large one, ironically. But when you're getting near a small black hole, the difference between the gravity at your feet and the gravity at your head is going to be immense. And that's what we call tidal forces. It's the reason why we have tides on Earth, is because the moon's gravity is going to pull more on the side of the Earth that's closer to the moon than the side of the Earth that's further away. And so we get a bulging of the water because there are different levels of gravity. In this case, your head is experiencing significantly less gravity than your feet because your feet are closer to the black hole, and that's going to pull you in faster, and that's going to literally rip you apart, where it's going to be ripping and pulling you down so that you form a string. Now, the ironic thing is, again, if it
It
was
will
a
be at
really
the
big black
spaghetti.
hole, it would be more even gravity over your whole body. And there's a way to create a wormhole, which is not the same thing as a black hole, where you can possibly avoid a lot of that tidal forces as you enter into the wormhole, and that would be your hopefully best outcome.
What's the difference between a black hole and a wormhole?
On a wormhole, you might actually get out. A black hole, it's a one-way trip.
Well, they say on the other side of the black hole is a white hole. You just spit out the different.
Yeah.
universe. So now let's come back to time. There was a time, that's oxymoron. There was a time that there was no time.
Hmm.
Will be a time that there is no time.
Yes. And the thing is that remember we said the definition of time is what you measure on a clock, right? So in the beginning, before the universe, there were no clocks because there was nothing to create a clock. There was no electromagnetic frequencies or anything like that. If you assume that the universe just keeps expanding and expanding forever, at some point, you're going to get to the point where everything is kind of frozen out. All of the atoms have spread out so much, and the average temperature of the universe has dropped so low that nothing oscillates. There are none of these processes working anymore. And in that sense, you could say time has disappeared because there's no clocks, nothing to actually make anything work.
I had a theory long time ago, and my math is not good enough to calculate that. But David, maybe you can calculate it for me. Imagine this. Let's say that we are talking about the big freeze. We are talking
Yeah.
about the universe. I'm in trillion, not trillion, like a Google billion years. Everything becomes so spread out, and every universe becomes so cold that we get as close as possible to absolute zero, to Bose-Einstein condensate. And that the math of it, the way it works is that we know if you have a system that you're at absolute zero or close enough to that, that system doesn't have a, like, it's not this atom or that atom, it's not David and Hammett, it is, we'll become one.
Hmm.
Our waveform is not close, but it's identical. It's the same waveform that described me and you. Right now, we are separated by time, by energy level, by temperature. You have your waveform, I have my waveform, and we are two distinct things. Our atoms are literally atoms inside of us are distinct things. That's how they react. But once we get so close to the absolute zero, no matter where you are, no matter where I am, we become one. Now imagine this vast universe that has spread out unimaginable amount of, separated, but everything, when they get too close to absolute zero, the entire universe becomes a Bose-Einstein condensate. Does that mean at that moment, the space between those, whatever they are at that point, they're not even particles, they're
Right.
photons maybe. Does it mean the whole space becomes irrelevant, goes to zero, and then all of a sudden it flips again, that the space becomes zero, if that vast space becomes zero and the whole universe become a white hole?
That's a good way to put it. But yes, I mean, effectively, this is one of the reasons why people study fundamental quantum mechanics and quantum gravity is because they want to be able to answer a question like that, is that what is the role of space? I mean, if you have no time, do you have space? And the definition of space is basically um, it almost requires you to have time because you can think of any time you have an interaction between two particles, that's an event. And space could be the distance between these events, where time is like a distance in another direction. So, yeah, you're right. I mean, but we also got to understand at that point, um, how does gravity factor into it? Like, as does space even exist at that point because time doesn't exist and you can't really define a space between points. And so,
But there is this,
and what happens then?
conservation of momentum and mass that says even though space is so spread out and so on, the mass is not lost, right? Is that correct?
Right.
The mass is not lost. It's just spread so out that the temperature right now is 3 Kelvin in the universe, or 2.7, right? That's
Hmm.
standing. But that temperature, let's say, by the way, 2.7 is astronomically higher than the Bose-Einstein condensate.
Right.
So the coldest place in universe is not in universe, it's in one of our labs, somewhere in one of
Yeah.
the universities.
Yeah,
And
and that's the thing. We can actually 2.7 degrees Kelvin, that's like liquid helium temperature. We can actually create that very easily in a undergraduate physics lab
yeah,
in a without even trying hard.
but when the universe becomes so much colder than it is now, and that process is going to take a lot longer than it took to go from where it was to 2.7. That
Mhm.
process is like a Google year or something, I understand. That
Yeah, it'll take a long time because it's dropping off
Mhm.
slower and slower. And so it's again, it's like, will it ever get to absolute zero? It's I don't know. But
Eventually,
it's going to get close
follow
effectively.
if you follow the math, it gets very close to that. But I'm not talking about the absolute zero. I'm talking about like in the moment that the whole existing universe becomes a Bose-Einstein condensate. At that moment, I think the whole universe is described by one waveform and one
Mhm.
waveform only. And that waveform, I think, if you, again, my math is not good, but help me out here. That if the entire universe is just one waveform, one particle, isn't that like a Big Bang? What is it?
Um,
Where are we there?
well, see, the thing is that Stephen Hawking tried to find a waveform for the universe, and I don't think he ever did. He also spent a lot of time trying to study the nature of time. And
While he was womanizing in a wheelchair, right?
right. And the thing is
We
that
are human as well.
yeah, and the problem is that we can't it's very difficult to get there because of noise. And so you're right, when you eliminate all the noise, then you can get down to one waveform. But then it brings down fundamental questions about the relationship between quantum mechanics and space-time, where the latest was that Roger Penrose, well, there's a couple, before that, there was a paper that came out by a guy named Oppenheim. And he
What,
basically,
Robert Oppenheim? Or
no, not Oppenheimer. Oppenheim.
I see
Yeah,
different.
Oppenheim came out with a paper where he basically argued that we're kind of on a fool's errand looking for quantum gravity.
Okay.
That the reason why we haven't found quantum gravity is because it doesn't exist. And he showed how we can have a quantum universe, quantum particles existing on a classical space-time, as long as there's certain uncertainties in the space-time that will allow it to work. And so this was a really revolutionary paper that just came out within the past year.
Okay.
And then there was I think on a podcast, Roger Penrose basically said that he thinks we've been going about it all wrong. Instead of quantizing gravity, we should have been trying to gravitize quantum mechanics.
Oh, that is
And
an interesting
he
way.
basically said that when we have this collapsing of the wave function in quantum mechanics, which is what we do every time we make an observation, what may be really going on is a gravitational effect. And so that's why it is that when we have, before we've observed a wave function, there's really nothing there. But then when we gravitize it or collapse the wave function, then it becomes something that can exist in our space.
Yeah.
And so there's the beginnings of thought on this idea that maybe we've been looking at it all wrong. I mean, and basically going all the way back to when Einstein was first trying to find quantum gravity back in the, 1930s, so 100 years, we've been on the wrong path. And so when you start looking at it like that, then this question about the wave function of the universe, what happens at the end in terms of everything having the same wave function, it kind of depends on the answer to that. Like, is there quantum gravity or is there not? And and then how do you fundamentally define what space is
Yeah.
especially in the absence of time. And and so this really, really becomes an interesting question.
Yeah, but I think that reminds me of an old mythological story that Rumi actually compiled it in a poem. I think original one of that was a Indian story, Indian mythology, that they have an elephant in a room and they sent some wise people in this dark room with the elephant, and every single of them they touch one part of this elephant and they describe, this is a trunk, this is a branch, this is a this is that. But and I think what we describe as, time, space, energy, and gravity, electromagnetism, and so on, I just naturally want to believe that these are different aspects of the same thing that we in the dark, we're just looking at that and don't understanding the true underlying things. Like, imagine if you're in a baseball, if you're an alien, you're in a baseball um, game, and you don't see anything but the ball. And you see the ball is just moving in a random way, and you try to describe the behavior of the ball, you come up with different aspects, like, how high it is or how fast it goes and so on. But the underlying game is what put everything together, that as hard as we try, I don't believe our biology is really made to understand that. And that actually, I think that's a sad part of it, that I don't believe we are going to, I personally don't
Yeah.
believe we are going to solve, at least not in my lifetime, not with my brain capacity or human brain capacity at this point, what that underlying thing is that give meaning to all of it.
Yeah, and that's the thing is that that's why we've been on this quest for a grand unified theory. And that's been a long time people have looked at that where they wanted to unify because they were able to unify three of the four forces of nature, the strong, weak, and electromagnetic forces, into the standard model of electromagnet, a standard model of physics.
Yeah.
And then they wanted to bring in gravity, and they created string theory as one idea, and it never really worked. And then they tried to go with M theory or membrane theory, and we've tried all this, and we've never really gotten to a good unified theory that brings the gravity into it. And then people tried loop quantum gravity, which was a different way of quantizing gravity, and that hasn't worked. And that's like I said, that's why we're at this point now of maybe saying, well, maybe that was all the ways the wrong path. And now we're looking at having our classical gravity and then having this quantum stuff that exists on it, and it's a different thing. And then that raises the question of why. I mean, why was the universe designed in this particular way? And it works. I mean, it functions, and if it didn't function, we wouldn't be here to have this conversation.
And some
So,
say
yeah,
the only reason that it works the way it is, because if it wouldn't, we wouldn't be thinking about it. So, and the
yeah.
homorphized version of the universe, that all these varieties exist, but only in our current version, it allows us to exist, to think about it.
Right. And then also on top of that, you've got rules and then you have parameters. Like there are fundamental rules and the equations we use to describe our universe, but then there's not a rule that says that the mass of an electron should be what it is, or the mass of a quark should be what it is. So that brings us to a question of, is there a larger rule that explains that it has to be that way, or are we part of a multiverse where each multiverse has different parameters that have been sort of tried out?
And some people,
And
God, that look at those numbers. If they
Mhm.
would vary 0.00003%, none of this would exist.
Exactly.
Rule that says it should be that, it could be any value. And so, intelligent design right there, that God made it that way, because in no other way it was even a chance that any of that would lead up to stars, galaxies, universe, atom, even that would make us exist.
Right. And Lee Smolin had this theory. It was called universal evolution. And the basic idea was that when you have a universe, the universe produces black holes, and inside the black holes can produce baby universes. And so a successful universe is going to produce more black holes, will produce more baby universes, and you can get effectively an infinite number of these. And each one is basically an attempt at trying out different parameters. And there's a natural selection that happens when the more successful universes are going to be produce more black holes, which produce more baby universes, which get the more parameters that work,
So
and that we eventually
almost like
show up.
biology.
It's like a biology system. I mean, the problem with it is that for it to work, you've got to have mind-bogglingly high numbers, and it still doesn't explain kind of the first mover on why certain things work, and also why we have a certain framework of gravity is going to work like this, and then these quantum mechanical forces are going to work like that. And it just kind of gets down to the parameters. So it's a lot of questions about why that would work. But again, if you've got infinite time because you've got infinite universes and you've got infinite trials, then you can make a system work. Just like with biology, is that if you have life and it's functional and it doesn't get snuffed out and it keeps reproducing, you can try out these different combinations of genes and eventually you get to some kind of intelligent life that doesn't kill itself and you can make things work.
Let's talk about that.
Mhm.
Do you think the universe is infinite? And if you no, number one, do you
Yeah.
think universe is infinite? And in this infinite universe, a bigger intelligent, like a medium being the universe, do you think that infinite universe has developed a consciousness that yes, there is this bigger consciousness in universe because it has existed so long that
Yeah.
and so if you give it enough time to any process, obviously it's proven you and I exist, you and I think, you and I have intelligence. Do you think universe has created, even if it wasn't an existence of intelligence before, do you think universe has an intelligence now?
Well, it's a back up to a few things. First off, in order to get an infinite universe, you really have to have a multiverse. You can't, within our universe, we know it has a definite start time. It has a definite finite time. We can only see so much of the universe, but we do know that it hasn't been around forever. So it's not really infinite. If we want to talk about intelligence, I mean, we got to really, really start and go back and think about what do we mean by intelligence? I mean, is intelligence consciousness
Yeah.
or is intelligence the ability to do calculations?
Well,
Because
universe does calculation.
yeah, the universe does calculations just like artificial intelligence does calculations. The thing with artificial intelligence, though, it has no agency. The reason why humans have agency comes from kind of our emotional responses to things and our, it's seriously like if you look at system one and system two in psychology, that what is it? Thinking Fast, Thinking Slow by I'm blanking on the name of the author. Um, Daniel Kettleman. It talks about how, we have these two systems of thought where there's the emotional intuitive system and there's the computational analytical system. And it's like our artificial intelligence only has the second one of those. So if you could have the most brilliant intelligence in the universe, artificial intelligence, it'll just sit there until you give it a command because it doesn't think that doing X instead of Y, there's any reason to do it. Uh, but going back to the universe, it's like it's calculating. It's when it creates a black hole or when it's creating a star or galaxy or solar system,
Yeah.
it's almost like it's running calculations
Do you
and
think universe has
computing.
consciousness?
I don't know. I don't know about consciousness. I know about intelligence and calculation, but I don't know about consciousness.
Okay,
I
that's
think
it.
For consciousness, I think you need to have that agency, and I don't know that it would have that.
Well, well, I can tell you a very limited system, Earth, which
Mhm.
is minuscule, it's meaningless. By having the entropy of sun passing through us in a very small period of time develop life, and in a minuscule time frame has developed consciousness, agency. We are talking. You and I, we
Mhm.
are talking. We think, so we are. So it is unimaginable to me that something so much bigger and so much older that entropy is passing through hasn't have developed consciousness. It
Yeah.
is for me mathematically. I think if I was a theologian, this would be my proof of God saying that the universe is so old and so vast, and there is so much entropy passing through. The fact that human has existed on this planet in such a short period of time is the proof that statistically it's impossible that bigger consciousness hasn't, even if it didn't start from the beginning, that now exists.
Yeah, and
Statistically.
also another argument for consciousness is that when you have, like I said, you have these algorithms or equations or whatever you want to call them, and you have the parameters. Even if you could explain the parameters through trial and error, it still doesn't explain the equations or the algorithms. A consciousness does. So it's kind of like if you're going to have a computer, um, you know, having the computer program needs to come from somewhere. And we haven't figured out a way that you can get to that program without something being put in it to start with.
Yeah,
That's one of the things. That's one of the big unanswered questions
yeah.
of how do you get that?
While talking about time, we are coming now to the time. Even for hours and hours, I think we are. There are so many the new questions we started talking about time that I'm hoping that we can continue talking about in one of our future, no, I think podcasts. I would love you to come and talk about the this algorithm of the AI or quantum computers and so on. But I think we should call it a day today. Thank you for joining me, David. It's always very mind intriguing and have an actual physicist talking about this, not an no layperson like me. So for everybody, please join us our future Essence of Science podcast. Thank you for joining us. Thank you, David, for joining us as well. I'm Dr. Abbasi for Essence.
Yeah, thank you. Thank you for having me, and I enjoyed this time talking about time.
Thank you. Bye bye.
Bye.